welcome back. We are studying AC bridges, and in our last class we talked about product bridge and ratio bridge. The idea is, if you make your bridge either in the form of a product bridge or a ratio bridge, then the balance equation becomes very simple to derive. Okay. So, in the last class we took some example, and the last example was about measuring an unknown inductor, lossy practical inductor which has some resistance also, which could be just the coil resistance. So, this is not pure, and we found that the simplest bridge that we can use to measure this is this one. This is a product bridge because two opposite arms Z1 and Z4 are pure resistance, okay. And this is a RC parallel combination. Why parallel? Because in the equation we have the term Y3, admittance of this branch, and admittance becomes easy to compute if the elements are in parallel, because you can simply add the admittance of the this resistor and this capacitor to get the total admittance, whereas it is easy to compute total impedance if the elements are in series. Now, today let us take another example. So, example 5. By the way, just for your information, this particular bridge is called Maxwell's bridge. Once again, this is just for your information. You are not expected to remember or memorize these names and this particular structure, not at all. Okay. So, before we go to example 5, we will need to analyze this bridge a bit. Okay. So, suppose the unknown inductor is very close to an ideal one. Okay. What do we mean by that? We mean the quality factor, goodness is very high, Q factor is very high. Okay. So, unknown inductor has high Q value, Q factor. What does this mean? This means simply the RS resistance is smaller compared to the inductance part. Okay. So, this simply means RS is much smaller compared to the j omega ls or the magnitude omega ls for a given frequency omega. Now, if so, okay, then the angle of Z2, okay, then the angle of this complex impedance Z2 will be close to or very close to 90 degree, plus 90 degree, because this is inductance. If so, now what is the angle balance condition? The angle balance condition says that the sum of these two angles, which is 0 degree plus 0 degree, should be same as the sum of this angle and this angle. So, that means sum of this angle Z2 plus the angle of or let me write theta 2. Okay. The angle of this impedance Z2 is theta 2 as per our notation. So, now here theta 2 plus this angle theta 3, this should be 0 degree plus 0 degree equal to 0, which means theta 3 should be close to is minus. So, this is minus theta 2. So, that means theta 3 okay, I am not sure whether I was using this angle notation here previously or not. Be consistent to your notation whatever you choose. Okay. So, this theta 3 is close to, very close to minus 90 degree. When is that possible? That is possible only if this RC combination is almost like a pure capacitance, then only we can have the angle close to minus 90 degree. So, this should be almost like a pure capacitance. That means, this leakage if you call, so this R3 should be very high, or the conductance of this branch should be very low. Okay. So, this implies R3 should be very high. Okay. Now, there could be a problem due to this, because in a previous chapter we have seen that high resistances, high value resistances have I mean, they are difficult to measure. So, that means it is difficult to have variable, standard, high value resistance. Okay. So, high and very low resistances are difficult to achieve. So, if this is the case that R3 should be very high to get this bridge balanced, and if we do not have a high value standard variable resistance, then what can we do? So, this is the question. Suppose the inductance we are measuring is almost pure, which means to get this bridge balanced, I need this R3 to be very high, and I do not have in my laboratory a high value standard variable resistance. So, what can we do? What is the solution? So, the solution, okay, so this is the question. Now, the solution is, instead of using R3C3 in parallel, use a RC series combination. Use a series combination of R3C3 instead of parallel combination. Okay. So, how would that help? Because if you find the series equivalent of this, okay. So, if you find the series equivalent of this C3R3, series equivalent of this thing C are parallel okay. series equivalent of this, call it this, call it C3S R3S. Okay. So, given the value of C3 and R3, you can compute the C3S and R3S such that these two impedances are equal. Okay. This is what we did yesterday at the beginning of this AC bridges. Before we started AC bridges, we discussed how to find the equivalent of this branch, that means given C3 R3, how to find C3S R3S such that these two are equivalent. So, if you do that, okay, so we did it yesterday, then you can, so if you find the series equivalent of this, then we will see that R3S is a small resistance, while R3, I mean this parallel combination, parallel equivalent is a high resistance. So, let this be a small homework. Okay. You just have to find the equivalent CS3S R3S, and you will see that if R3 is high, R3 series will be small. So, I mean another way to visualize this quickly instead of doing this full derivation is that, so we want this to be close to a pure capacitor, because R3 is high. So, this combination is close to a pure capacitor, and here also that means this combination should be close to a pure capacitor, which is possible only if this impedance, that is 1 over j omega C3S, is much higher than this impedance, which is R3S. We want this to be more close to pure capacitor. So, that means here also these two are equivalent, here also it should be more close to a pure capacitor. So, this impedance should be small if this is high. That is easy to see, and you can do this derivation yourself to convince yourself, and I would be very happy if you do it. Okay. So, this is the solution. So, instead of using these two in series, use R3 C3 in parallel. Okay. So, the new bridge the modified bridge will have these two in series. Okay. So, and these are variables, of course, C3 R3, these are variables. So, now you can vary this, and with a small value of R3 you can get this bridge balance. So, this is the solution, and just for your information, this bridge is most likely called Hay bridge. Once again, you need not remember this. Okay, but then there is a small problem. What is the problem? The problem is, if we write the balance equation, so we can write Z1 Z4, the product, which is same as R1 R4. This should be same as the product of Z3 Z2. Z2 is the unknown. Now, so Z2, this unknown, we can write it as R1 R4 divided by Z3 or multiplied by Y3. Now, why admittance is difficult to compute when the elements are in series? Not impossible, not very difficult, but slightly difficult. So, what can we do? Instead, I mean, since this is difficult to find why admittance in series, and we need this in series definitely because we do not have a high R3. So, we have a small R3. So, we have to use it in series, no other choice, but here it is difficult. So, what is the solution? What is the trick? The trick is write this equation in this form, write it as R1 R4 multiplied by Y2 is equal to Z3, and or you can write Y2. So, this is the unknown Y2 is equal to Z3 divided by R1 R4. Now, Y2 will again be difficult to compute because these elements are in series, but I mean one trick you can do, I mean if you like, is model. So, this trick is model the unknown inductor as a parallel combination of an inductor LP and RP. Okay. So, like this. By the way, this is in series due to the reason already mentioned. Okay. So, let us model it this way, and then the balance equation becomes simple. How? So, let us write it this way: R1 R4, this product should be same as the product of these two impedances. So, which you can write as Z3 and multiplied by Z2, but we can write Y2 here, and from this now Y2 is same Y2, which is same as 1 over Rp plus 1 over j omega Lp, okay, admittance of this, and that means the conductance plus susceptance, and this should be equal to Z3 plus Z3 divided by R1 R4. So, 1 over R1 R4 in place of Z3, write it as R3 plus 1 over j omega C3. Okay, and this will imply, now equate real to real. So, 1 over Rp is this. So, that means Rp, you can write this as R1 R4 by R3, 1 4 by 3, and 1 over Lp. So, or Lp you can write this as R1 R4 multiplied by C3, right, R1 R4 C3. So, just in 2 lines, once again just in 2 lines we can find the balance equation. Okay. So, the main trick is model this unknown inductor in parallel combination, and then if you really want to represent this unknown inductor in the form of a series combination, you can finally find the series equivalence or equivalent circuit of this LPRP. That trick we have seen yesterday, how to convert a parallel RL combination into its series equivalent or a series combination into its parallel equivalent. That trick we have seen yesterday. Okay. So, this is called Hay bridge, and all the things that we are doing is not a new science, it's nothing new, it's all small mathematical and engineering tricks which makes these things easy and simple. Okay. So, we are just learning small tricks which make the bridges easy to derive their balance equation. That is the point. We are not doing any new science. So, in that sense this is a bit boring too, but if you do it following this trick of product and ratio bridge, calculation becomes simple. It is even simple during the exam, because you can find the you can design the bridge, you can find its balance equation all in 2-3 lines. Okay. So, now let us take another example, example 6 I guess. Let me describe a situation. The situation is that we want to measure a capacitance, an unknown capacitor. So, we want to measure an unknown high voltage capacitor. So, a capacitor which is meant to be used in some high voltage application. So, some high voltage will be applied across this capacitor and it will work under that situation. So, how will it perform? So, how much will be the leakage etc. under that high voltage, stress? That is what we want to measure. Now, if the capacitor is supposed to work under a high voltage stress and we want to measure its performance, then we should also do the measurement under similar high voltage applied across it. We cannot measure the capacitor with a low voltage across it and get its RC values and say that this is the RC equivalent. No, because its performance will change when this capacitor will be used under a high voltage stress in the real scenario, because simply speaking, under high voltage stress leakage current may increase. Okay. So, therefore, its performance will change. So, to get an actual evaluation or feeling how will it work under high voltage stress, we should measure it only under a high voltage applied across it. Okay. So, we want to measure an high voltage capacitor. So, we will use some bridge, of course. So, let us draw a bridge. We have to design this bridge. But now, this unknown capacitor RC, if you want to represent in parallel, let us put it like this. Call this Cx, Rx, unknown capacitor, And now we have to design or find what this other parameters are, other branches are. Okay. Now what can we do? So one solution that we already have seen is just use a ratio bridge and make it like this, pure RR, and here put a RC combination, parallel or series, whichever is convenient. I think parallel combination will be convenient here. Now to get it balanced, what we need? We need to vary these 3 arms. This is Z1. Now we may not need to vary all these 3. Okay. We may choose to vary just maybe these 2. That's sufficient. So we may or choose to vary these 2. That may also be sufficient, because we have 2 unknowns. 2 unknowns. See, number of unknowns is 2, Cx and Rx. So we need 2 controls. We need 2 variables or 2 controls at least. So we need not vary all these R's. I mean, these are this C, these are this C. There are too many variables. We may keep some of them fixed, no problem. Okay. But definitely we have to vary this capacitor, because if we choose to vary, for example, only these 2 resistances, okay, then the number of variables, yes, is 2. If we just choose to vary this 2 and keep it constant, then number of variables is 2, number of unknown is 2, but we cannot possibly get a balance, because we won't be able to change the phase angle relationship, because this angle or call it theta 3, 1, 2, 3, 4. So theta 3 minus theta 4 is always 0. Is always 0 if I just choose this 2. Okay, these 2 to vary, and this one is fixed. So the theta 1 is fixed, theta 4 is also fixed, because this is the unknown one, we have no control over it. So we cannot, and this is not going to this is not going to change, and we need theta 3 minus theta 4 equal to 3 minus 4 equal to 1 minus 2. Okay. So right side, this side is fixed, and this side is 0 always. You are just changing this. Okay. So we will never be able to change this equation. So to be able to change this equation, I mean get this equation satisfied by changing something, we have to change theta 2. Okay. So sorry, we have to change theta 1, because then only we can adjust the right hand side and get the right hand side equal to 0, left equal to left hand side. Okay. So we have to definitely change this branch. Okay. So we must have Z1 variable. Okay. Now yes, so we can choose Z1 to be variable, and maybe we can choose either of this Z3 or Z4 to be variable. We don't need to vary all 3. We can choose Z1 to be variable and Z3. Z1 and Z3 is fine. Z1 and Z4 is fine. But Z1 has to be variable. If we cannot vary Z1, then we cannot vary the difference between theta 1 and theta 2, and we cannot make it equal to 0. That is what we need. Okay. I hope this much is clear. And then now the next important point is this. This capacitor is under a high voltage. Okay, we have to test this capacitor with a high voltage across it. So, if we we can put the supply like this, then some voltage drop will happen across this branch, some voltage drop will happen across this branch. Okay, and the sum of these two, phasor sum, will be same as this voltage. Let me take this as the reference, call this as V phasor. So, this point is at V. Okay, and now if this voltage, call it V branch 1, 2, 3, 4, call it V 2, and this voltage branch 4. Okay, so V 2 plus V 4. Okay, so these are phasors, should be equal to V supply voltage, and V 2 has to be high. The magnitude of V 2 should be high. Why? Because we want to do this test with a high voltage applied across this capacitor. Okay. Now, if so, under balance, so at balance we know that this voltage across this branch, call it V 1. Okay. So, at balance or near balance, the magnitude of V 1, this voltage will be equal to this voltage, close to this voltage. So, near balance, the magnitude of V 1 will be that branch is V 4, or sorry, this is V 2. Okay. So, these two voltages will be equal, and this is a variable arm, Z 1 is variable. So, that means we are adjusting this Z 1, and the voltage across Z 1 is very high, near balance, and somebody is manually, I mean some person is adjusting this voltage. So, this is risky. So, this is risky. So, Z 1 is variable and voltage across it is high. So, it is risky to operate, to perform this experiment, to perform this measurement. So, what is the solution? The solution is what is proposed by shading this person, this man, proposed a nice solution which is not risky. So, his idea is called shading bridge. You need not remember these names, etc. Just see how nice the idea is. The idea is, he said, I will have I will adjust only these branches Z 3 and Z 4. So, I will have only these two branches variable and keep Z 1 fixed. So, shading solution is So, this is the bridge. So, here we have Cx, Rx, this unknown, call this Z1, Z1, Z2, Z3, Z4. Okay. So, setting said that we will keep Z1 fixed and design a bridge where we need to vary only this Z3 and Z4, and the supply voltage is like this. So, this is high voltage, this is a very high voltage, okay. But we will ground this point. This is not just a reference point, this is really grounded, earthed, okay, ground point. Okay. So, this potential is really the earth potential or 0 potential. So, this value is really 0 volt with respect to the earth, and therefore, this potential is very high, V, very high. So, this is V, very high, and V is equal to phasor sum is this V2, okay, plus V4. I am not drawing V2 and V4, but the meaning is clear, V2 across Z2, V4 across Z4. Okay. So, V is very high, but we will choose V4, that means this voltage across Z4 to be small. Okay. So, we will have V4 small, then of course then V2 and V of and also V very high. Okay. So, this is small, this is high, this is high. So, high plus small is high, no problem. Okay. So, we need this to be high, we will have this high, V2 high, we will maintain this value V4 small, and this is the variable arm. These two are going to be variable arms. Okay. So, therefore, the person who is adjusting this, he is operating a voltage V4 which is close to ground potential, risk is much lower. Okay. So, this potential, call this potential this value, call it VA. Okay. VA will also be close to ground potential, earth potential. So, risk will be small. So, this was Sering's idea, that design a bridge such that we can keep this fixed, Z1 fixed, and have only these two variables, so that then we can maintain, we can ensure that the operating person is varying the this Z4 within and this voltage is within a lower value. Okay. So, now how can we do that? Okay. Now, the goal is to design a bridge such that we can keep this fixed and we can vary only these two. How to do that? Okay, so let me draw this, let me give you the solution. So, this is the unknown branch Cx Rx unknown, this has to be a fixed impedance, we cannot change it. These two will be variables. Now, we have to decide what to put here, resistance, capacitance, inductance, what to put here and what to put here. Okay. Now, this is a small question, you may think yourself, okay, and find some solution. You may pause the video at this point, and now I am giving a solution which Setting proposed. Setting proposed that let us have a capacitor C1 pure here, and let us put say a resistance. Okay. So, what do we put here then? So, what can we put here? So, this angle is 90 degree minus this angle is always 0 degree. This angle is between somewhere between 0 and minus 90. So, what can we put here such that the sum of this and this angle is same as the sum of this and this angle. This two sum is minus 90. So, this two sums should also be minus 90. So, this is negative, this also has to be negative angle. So, what we can put? We can put here a RC combination. Variable RC combination. So, call this is branch 1, 2, 3, 4 according to my notation. So, we will choose this as some combination of C3 R3. Okay. Some series or parallel combination of C3 and R3. Okay. Now, you see, observe, firstly we actually have designed a product bridge. This is a product bridge. Why? Because this Z1 times Z4, okay, is a pure imaginary number, purely imaginary, and this is equal to, if this I call as R4, this is equal to R4 divided by j omega C1, purely imaginary. You can write this also as minus R4 by omega C1. Okay. So, this is a purely pure imaginary number, product of two opposite arms, purely imaginary, and we have seen when the product of two opposite arms are purely imaginary or purely real, we call it a product bridge, and such bridges are easy to find their balance equation. So, this is a product bridge. Secondly, this is point 1, point 2, angle balance condition theta 1 plus theta 4, which is of course same as minus 90 degree, can be equal to theta 2 plus theta 3, where this is between 0 and minus 90 to 0 degree, and this is also between minus 90 degree and 0 degree. This is minus sign and this is an hyphen. Okay. So, we can get this balanced. So, this is the nice design what shading proposed. Once again now, and point 3, by varying C3R3 we can vary this angle relationship. You can vary angles. Okay. So, all requirements are fulfilled. Now, let me finally finish this by finding the balance equation. Now, let us once again, this will be very simple. What can we write? We can write Z1, Z4 same as Z3, Z2. Z2 is the unknown, and Z1, Z4 this is equal to 1 by j omega C1 multiplied by R4. Now, now we have to know whether this is a series combination or parallel combination, and whether this is a series or parallel combination. Okay. So, let us choose. So, we choose, we have many options. So, we choose C3 R3 to be in say parallel, just a choice. You can choose it the other way. Okay. So, we choose it to be in parallel. So, R3 C3 and these are variables. So, I am putting these arrows. Okay. So, we choose this to be in parallel. So, then this unknown one will be let us see what we can do. So, let us here then we can write this as Z2 multiplied by on this side we write Y3. Okay. So, Z3 we bring on the left side. So, we have Y3 there, and from this we can write R4 by j omega C1, and Y3 is nothing but 1 by R3 plus j omega C3. This should be Z2. Now, it will be easy if we think this in series combination. Cx Rx. So, then we can write Rx plus 1 by j omega Cx. Now, you can equate the real part to real part and imaginary to imaginary part. We will have two equations. First equation, say this part, which is the imaginary part, that gives R4 by C1 R3. Here we will have 1 over Cx, and here the real part is R4 C3, R4 C3 j omega cancels. This side we will have Rx. So, these are the two balance equations. Rx is this, Cx is 1 over this. Okay. It's very simple, just two lines once again. Okay. So, and if you had chosen to use a RC series combination, then it would have been easier to model this in parallel form, and then if you want to of course convert one form to the other, you know how to do it. So, here we choose to use C3R3 in parallel. Okay. So, in the laboratory we will use a parallel combination of C3R3 and therefore, we model Cx Rx in series. Okay. So, the point is, we have initially learned that any Cx series combination can be modeled as an equivalent another Cx parallel combination. Why did we do that? Because now when we are studying AC bridges, bridges become very easy if you choose sometimes some elements, some branches as parallel combination of Cx, Cr or series combination of Cr. So, that depends on the situation, and then using what we learned previously, we can convert one result parallel combination into the series combination or series combination into the parallel combination. Okay. So, this is the this all we are doing are mathematical tricks, okay, how calculations become easy and simple. Okay. This is not a new science, these are all tricks to have calculation simpler, and we are giving you practical situations under which this type of scenarios may arise, like when we are measuring an unknown inductor, but we do not have a standard inductor. So, what was the solution? The solution was the Maxwell bridge, which we studied before. Then we gave another practical scenario, like we are measuring a capacitor under high voltage and we want to eliminate the risk of this experiment. So, we saw another bridge. Okay. So, these are some practical situations and we are applying mathematical tricks, common sense. I mean, I do not know how interesting this is, maybe not. Yeah. So, thank you.